In the previous class, we discussed about diffraction of light at spherical surfaces, and also we derived Lenz-Becker's formula and Lenz formula. Now we discuss what is known as the power of a lens. Power of a lens. It is nothing but the amount by which a incident beam is deviated from its path, that is either converged or diverged by a lens. If the path of the incident beam is altered by refraction of a lens, the angle by which the path is deviated by the lens is defined as the power of a lens. We will see mathematically how the power of a lens is expressed. Let us consider a converging lens. Suppose a convex lens. A beam of light striking at a point at a height h from the optical center. So say here it is after refraction passes through the focus, because I have taken a parallel beam and is refracting through the lens, passes through the focus. So this distance is nothing but focal length. Now instead of going like this, the path of the beam deviated by an angle delta. So suppose that angle is delta. Now from the figure we can say that tan delta is equal to height at which the beam strikes the lens by the distance at which the image or the ray crosses the principal axis. So here in this case it is f. So the tangent of the angle by which the path of a beam striking at a distance on the lens after refraction, how much it deviates, that angle is expressed in terms of the height at which the beam strikes the lens and the distance at which it crosses the principal axis. So from the figure you can write like this: tan delta is equal to h by 5. Suppose if h is taken as 1 unit, let us suppose 1 meter, and for small angle of delta, tan delta can be written as delta, that is equal to 1 by f. So if the distances and they are measured in meters, the power of a lens is expressed in diopters. So for f is equal to 1 meter or 100 centimeters, the power of a lens is said to be 1 diopter. That means a lens of focal length of 100 centimeter will have 1 diopter power. Now a converging lens has positive power, a diverging lens will have a negative power. For example, if the power of a lens is said to be plus 2.5 diopter, then the focal length is given by 1 by 2.5 meters, or that is 40 centimeters. So the power of the lens is 40 centimeters. So like this we can define the power of a lens, and its unit is diopter. Positive lenses or converging lenses will have positive power and diverging lenses will have negative power. Now we will talk about the combination of lenses. That is, lenses can be put together in order to achieve more magnification. Such a combination of lenses are used in cameras, telescopes and other optical instruments like microscopes also. Now, consider two lenses, thin lenses combined like this of focal length f1 and f2. Suppose their optical centers coincide. Now, what is the effective power of such combination? That is what we are going to see. Now, suppose if you have an object here, the image due to which will form, say, at some position here, O dash. But due to refraction by the second lens, the actual image will form somewhere here. So, if this is U, from the center of the lens combination, and suppose this is, say, some V dash, and this is, say, some V. That is the final image distance from P. Now, from lens formula, already we derived it, we can write for the first lens 1 by V dash minus 1 by U is equal to 1 by F. And for the second lens, we can write like this: 1 by V minus 1 by V dash is equal to 1 by F2. Here, the image formed by the first lens acts as an object, virtual object to the second lens. Hence, you will get the final image. Okay. So, with the combination of lenses, what happens? Focal length decreases. So, the image is formed nearer the lenses. So, by increasing the number of lenses, what will happen is the effective focal length changes, and you see what happens according to this formula. You can see it mathematically. Now, adding these two, what happens? These two gets cancelled, and finally 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2. So that is, the system acts as a converging lens of focal length given by this formula. So effective focal length decreases, that you can observe from this formula. Suppose if you combine a convex lens and a concave lens of equal focal length, that acts as a glass slab, because the focal length becomes infinity, so the power will be zero. The power will be zero, so it won't show any magnification. So actually this is algebraic sum. So the effect, reciprocal of the effective focal length is algebraic sum of the reciprocals of focal lengths of the individual lenses. For converging lenses, take positive sign for the focal length. For diverging lenses, take negative sign. Okay, similarly, the power of the combination is given by P1 plus P2. So, for converging lens, power is positive. For diverging lens, it is negative. Now, we know that the image formed by the first lens acts as the object for the second lens. Therefore, the effective magnification due to combination of lenses can be written as product of magnifications due to the lenses in the system. So, this is about effective magnification or effective power of combined lens systems. Okay. So, next we will discuss the refraction of light by a prism. We discussed just now about the power of a lens. Now we are going to discuss about refraction by a prism. So the concept power of the lens is a very important 2 marks question. So therefore, you must make a note of it, and several times it was given in the exam. The power of a lens is defined as the convergence or divergence by a lens of light incident on a lens at a unit distance from the optical center, so which is expressed in diopter units. The power of a lens of 1 meter focal length is said to be 1 diopter. For positive lenses, the power is positive. For diverging lenses, negative lenses, it is negative. Now we will discuss about refraction of light by a prism. So here we consider a prism. The cross section of the prism is shown like this. So this is the prism, and AB and AC are the two refracting faces. This one, this one. Now consider a ray is incident like this at an angle at a point, say some P. Now the ray after refraction passes through the prism and comes out. So let us say this is some point Q. Then the angle of incidence is measured with respect to the normal drawn here. So this is the normal drawn, and this is the angle of incidence I1. Now similarly you draw a normal here, and this is say I2. In your textbook it is given as angle of emergency E. Now both these normals suppose meet at a point N. Now the path of the incident ray is deviated. Therefore, if in the absence of this prism, the ray would have traveled like this. But due to the prism, the path changed. So the path changed by some angle. So this angle by which the incident ray changes its path is defined as angle of divergence or the deviation. So I1 is angle of incidence, and here this angle is angle of refraction R1 inside the prism, and let us consider this as R2, angle of incidence inside the prism. So I can write R1 is angle of refraction inside the prism, and similarly R2 is angle of incidence inside the prism at say some point Q, and here I2 on E is angle of refraction at the surface AC or angle of emergence. Like that also we can say. Now let us derive a formula for refractive index of material of the prism. So that we call it as a prism formula or prism equation. Now you observe the figure, there is a quadrilateral. That quadrilateral, that is APNQ. So this APNQ is a quadrilateral, and in that quadrilateral total angle is 360 degrees. So, but whereas here there are two perpendiculars here, therefore this angle is 90, this angle is 90, because these two are normals. So these are normals, and they are meeting at the end. Therefore this angle and this angle 90 degrees. Therefore the sum of the opposite angles also must be equal to 180 degrees. So therefore angle A plus the angle at N, that is PN Q, I can say. So I can write like that also. PNQ must be equal to 180 degrees. Then in the triangle PNQ, in the triangle PNQ, you know the total angle is 180 degrees. Therefore, angle R1 plus angle R2 plus angle PNQ must be equal to 180 degrees. So now these two must be equal. So comparing these two, this angle PNQ gets cancelled. So what you get is that angle A is equal to R1 plus R2. This is what we get. Now similarly, when we talk about this angle of deviation, the total deviation is produced at the surface AB and also at the surface AC. So total deviation produced, that is equal to, so deviation produced here is this much. That is just nothing but the total angle I1 minus R1. So this angle minus this angle gives you this, because these opposite angles must be equal. Therefore, I1 minus R1 gives this angle. Similarly, the deviation produced here. So this angle is given by I2 minus R2. Therefore, I2 minus R2. That gives the deviation produced at Q. Therefore, total deviation produced is I1 minus R1 at surface AB at P and I2 minus R2 at Q at the surface AC. So that is the total deviation. Deviation produced by the refracting surface AB and the refracting surface AC. That is the total deviation. So that can be written as like this: I1 plus I2 minus R1 plus R2. But already you have shown that R1 plus R2 is equal to A. A is nothing but angle of the prism. The angle between the two refracting surfaces is called as angle of the prism. So therefore, this can be written as like this. So I1 plus I2 minus A. Where A is the angle of the prism. Now, if you go on increasing the angle of incidence, the deviation also changes. You can do some experiment and you can also draw a graph between the angle of incidence taking it on x-axis, angle of deviation on y-axis. So you might have studied about the experiment for drawing that ID curve, that is determination of refractive index with the help of pins and a drawing board and a drawing sheet. So by arranging the pins with the different angles of incidence for the prism and the corresponding deviation angles can be measured. Of course, you are going to do the experiment also in practicals. So for different angles of incidence, the deviation angles can be measured experimentally. You can do it with the spectrometer also, but in our laboratories that is not available. So we use pins and a drawing board with a plain white paper or a drawing sheet, and using that also you can arrange the pins so at different angles of incidence. Then you can measure the angle of deviation by observing the image of the pins from the other refracting surface. That you are going to do in the practicals. Then you will know how the experiment is done. Already I think you might have studied in your lower class. So if you do this experiment and you draw a graph with different angles of incidence and the corresponding angles of deviation, you will be getting points, something like this. So that means first the deviation decreases with angle of incidence, and later with increasing angle of incidence, deviation increases. So you may be getting a curve like this. So like this. Now, if you observe for any angle of deviation like this, you have two angles of incidence. This is I1. You can say the corresponding is angle of emergence I2, except at this point. So except at this point where both I1 and I2 become equal. For all other positions, you will have I1 and a corresponding I2. It means that for a given angle of incidence, there is a given angle of emergence. This is for different angles of deviation. You will get a similar thing. That it shows that if you change I1 and I2, that is, if a ray is incident at an angle of I2, the angle of emergence will be I1. That you can see. So it means that the ray is completely reversible. The path of the ray is reversible. So if a ray is going like this and coming out like this, it is equivalent to a ray incident like this, going like this and then coming out like at this angle. So since the path of a ray is completely reversible, we get for a given angle of deviation, you have same angle of incidence, the angle of incidence I1 and angle of emergence I2, and they are interchangeable. For angle of incidence I2, you will get angle of emergence I1, but at a particular minimum angle of deviation, they become equal. That is, I1 and I2 become equal for a particular angle of deviation, which that angle we call it as minimum deviation angle of minimum deviation. So at minimum deviation, the path of the ray inside the prism becomes parallel to the base. So the path of the ray becomes parallel to the base. In such case, R1 and R2 also will be equal. Therefore, the above formula can be written as like this. So therefore, since A is equal to R1 and R2, so A is equal to 2R. Therefore, R is equal to A by 2. And also, we can say that this dm is equal to 2I minus A. 2I minus A. Therefore, 2I is equal to A plus dm, or I is equal to A plus dm by 2. So here we got R is equal to A by 2 and I is equal to A plus dm by 2. Now we can use Snell's law of refraction to find the formula for refractive index. So what is Snell's law? According to Snell's law, refractive index of the second medium with respect to first medium is given by sine of angle of incidence in the first medium by sine of angle of refraction in the second medium. So using that, sine A plus dm whole by 2 by R is sine A by 2. So this is the formula for refractive index of the glass prism with respect to A. Now, if the glass prism is of small angle, so you can think of small pieces of glass as prisms with small angles of the order of say some 4 degrees or so. So in case of small angled prisms, the formula changes a little bit. In such case, sine of the angles will become very nearly equal to the angles itself. So in such case, n is equal to, I am dropping this subscript, therefore I am writing it as n for refractive index. So in such case, so this refractive index formula changes into a plus dm by 2 by a by 2. So that 2 gets cancelled, and this is equal to a plus dm by 2. 1 plus dm by 2. Sorry. So this is that 2 gets cancelled, 1 plus dm by a. So therefore dm is equal to a into n minus 1. So dm is equal to a into n minus 1. That is the formula for angle of deviation in case of small angle prisms. And a problem is given based on this formula, and you can see in the 2 marks questions. So that is a very important question. You must solve the problem, find out what is the refractive index of such a small angle prism. Say some 4 degrees or something is given, and you can find out for such a small angle prism what is the refractive index. Okay, with this topic is over. Then we'll go to the next topic. That is, in the next video we will be discussing about dispersion of light. Okay.